Problem states that we have a binary tree. As we can see, this is the binary tree that we have, and we have distances given. So these are respectively the distances. Now we have to find out all the different leaf node pairs. We need to find out what? We need to find out pairs in this binary tree such that the shortest path between them is less than or equal to some integer given to us as distance. So the shortest path, so over here in this example 1 we can see that 4 and 3 are the two leaf nodes. Now the shortest path between them is this, right? This is at a distance of 3. So we can say that 4, 3 fall in our result set. Result set of what? Of the pairs that we need. But what do we want to return? Just the number of pairs, nothing else. Okay. We can go through the other example also. If we see over here, we have 4 leaf nodes. Now if we see that the maximum distance can be 3, but if we go from this subtree to this subtree's root nodes, so ideally from 1 or 2 to 3 or 4, we can see that it is 4 at least, the distance between these leaf nodes. So between these subtrees only we'll have to find out. And this comes out to be 2, this comes out to be 2, the distance. So we can say that 4, 5 as well as 6, 7 will be in our tree. Oh, sorry, will be in our result set. Now our result set. But the count of this result set, over here would be 1, over here would be 2. That is what we have in the outputs. So now coming to the second point of discussion, which would be that if we have a binary tree, we have 3 traversals basically that comes to mind: in order, pre-order and post-order. Also we have lever order traversals, which is an iterative approach. Right now, what do we want to visualize first? The first thing that we want to know is, can we use one of these? The intuition that I get over here is, first point that I get over here is, first of all I'll have to look towards the left side of my subtree and the right side of my subtrees, and then come to the parent to choose whether I have such pairs in my subtree. So for example, if I take this example only of 2, 3, 4, 5, 6 and 7, what I'm trying to say is, if I take this subtree 2, 4, 5, what I would ideally need is from my right side, how many nodes over towards the right subtree do I have and at what distance. So right now I'll have one leaf node which is 4. So I have how many leaf nodes? One leaf node at a distance of 1 from the parent. Over here towards the left subtree also I have one leaf node at a distance of 1. So basically I wanted only these two values, right? That from my right side, how many leaf nodes do I have? From my left side, how many leaf nodes do I have? And at what distances? So I can consider that if I have an unordered map to do this, I can basically get, so at 2 from the right side, my 4, 2 will ask 4 that how many leaf nodes do you have and at what distances. So 4 will reply that you have one leaf node at a distance of 1. Similarly, 5 will reply to 2 that even here you'll have one leaf node with a distance of 1. Suppose if there was something like a 12 and a 13. Now when we come till 2, right? So we came down till 12 first, right? And then we went back to 4. Now 12 says that hey, you have one leaf node at a distance of 1 from yourself to 4 when 4 asks the question to 12. Similarly, when 4 asks to 13, how many leaf nodes do you have in this subtree and at what distances, it will also reply that I have 1 at 1. Now when 4 replies back, what it will say is I have 2 leaf nodes which are at a distance of 2 from you, which means it will say that at a distance of 2 you have 2 leaf nodes, whereas my right side will still say that it has 1 leaf node at 1 distance. Now what I need to look at is if the sum of these two distances is less than the distance given in the question. If it is, then it is a good pair. So if suppose the distance was 3 over here, then I can happily say that 12,5 and 13,5 can be the pairs, which means that it is a basic P&C problem now, that the number of occurrences towards the left side and the number of occurrences towards the right side both will get multiplied because each and every one is mutually exclusive. So what I mean by that is when I come to 2, I know that these two pairs 12,5 and 13,5 will be mutually exclusive from the pairs that I've already calculated. So suppose when I was at 4, I knew that 12,13 can also become a pair, right? 12,13 ka bhi distance is less than my distance between 12,13. It is only 2, right? So which is less than 3. So this is also there, a pair, but I have already calculated it. How do I know that this is mutually exclusive? Because everything whatever is considered towards the right side has already been calculated and everything towards the left is new in our calculation. So these two are basically mutually exclusive nodes that we are getting. So from the left side we are getting X number of nodes, from right side we are getting Y number of nodes, and all the possible combinations of these nodes can help us form the pairs. Now why post order over here? Because what I would want to know is from right subtree and the left subtree first, that how many nodes do they have, to decide whether I can include them in my good number of pairs. Now coming back to the recursion tree, how it will look like, I've already given the basic recursion tree, how it will look like, but we can just go over it again once. We'll take a bigger example to dry run now. Yeah, so this example will be dry running on. First of all, we go towards, it is a post order, so we go towards the left, we go towards the left, we reach here. Now 2 asks how many leaf nodes are there. It replies back, it says with 1, 1 ka unordered map. Again, now it comes to 5. It asks 5 the same question. It replies back with 1, 1 ka map. Now we know that 1, 1, so 4, 5 can be a pair, right? And 1, 1, so for each of these values and these values, so we'll run a for loop for each of this left map values, and then for each of the right map values in that. So we'll consider all the pairs, and then we'll check if the right map plus the left map value is less than or equal to distance. If it is, we know that we can do what? We can just answer plus right map frequency into left map frequency. So now what this will return to 1 is it will say, hey, I have two frequency at distance 2 from you, 2 leaf nodes at distance 2. Now 1 has gotten the left, now it will go to right. Again we go to the left, again similarly it will say, it will give 1, 1. It does not have anything towards the right, so there is no pair formation over here, right? There is no pair formation here. It will also return with saying that at a distance of 2 you have a 1 leaf node. Now it will go to 7, 7 will go to 9, 9 goes to 10, 10 returns 9 that, hey, I have 1, 1 leaf node at a distance of 1. Now it goes to 11, it comes back, it says that I have 1 leaf node at a distance of 1. Now 9 again reports back to 7 saying, hey, I have 2 leaf nodes at a distance of 2 from you. Now 7 has gotten something from the left, right? But before returning to the 7, 9 pe we are calculating. 9 pe will be calculating similarly in this case how it was, similar case here it will be there, and then we'll be returning that in the answer. Again we'll be doing plus 1 into 1, which is like 1 pair. So right now our answer is equal to 2, 1 pair from here, 1 pair from here. At 7 we do not have anything towards the left side, so it will return that to 3, that hey, you have 2 nodes at a distance of 3 from you. So now we have that we have 1 node at a distance of 2 and 3 nodes at a distance 2 nodes at a distance of 3 from it. So now 3 has 2 choices. It has 1 node at a distance of, this is distance, this is the frequency, and now 3, 2 in the map. Because if we see both the distances are 3, over here if 7 had something like 12 suppose, then this would have had another map also, but we do not have it right now. So distance, frequency. Now if we go in the for loop, the answer plus equal to will not happen, because a left map plus right map, which is like 2 plus 3, the distances, 2 plus 3 is 5, which is not less than our 3 value of distance, right? So this will not give us any pair. Similarly, if it does not give us any pair, right, when we go back to 1, what it will say to 1 that, hey, I have this 8, right? So I have at a distance of 3, I have 1 value, and at a distance of 4 I have 2 values. So this will be my map now, right? So now I'll try with 2 comma 2 with this and with this also, but I know that I will not get anything because 2 plus 3 is also greater than 3 and 2 plus 4 is also greater than 3. So this will also not contribute to my answer. So my answer will have how many? This is the one thing which is less than 3. This is the other thing which is less than 3, and nothing else is less than 3. No distance between two leaf nodes is less than 3. Right. So now when we are returning, what do we return? After doing this is for the answer. Now we have to return a map, right? We said that we will be returning an unordered map of int comma int. Will be returning this. Suppose I'll name it as empty. Now what will this map have? Map will have all the frequencies from below at the distances, but the distance will become +1 because we are returning it to the parent. Till here we have the distances, we'll be doing +1 to that distance to return it to the parent. So for each of the values in left map, we will check if the left map ka distance, right, is less than distance, because if it is greater than distance already, then however we cannot have the answer, right? Because if this value, if one of this value is also greater than 3, my distance, then this plus this will anyways be greater, right? So if it is greater, if distance say less है मेरा distance node का current map का distance, only then we'll be giving it in the return map. So in the return map, I'll be giving the map of the whatever distance was there, right? But distance +1 I will do, and then I will plus, because I know that for that much of distance plus equal to the of, I'll make it in the other line so that I'll understand it better. So map of the left map का जो भी distance था +1 I will do, and I will plus equal to the left map का frequency. Now why I am doing this is because suppose from the left map you will have that you have 3 nodes at a distance of 2. This you got from the left child. From the right child also you might have that there might be 5 leaf nodes at a distance of 2. I'm just saying this might not be possible, but if it is possible in an n-array tree it will be possible. So suppose, okay, taking one only as the example, as like one frequency from the right child. Now 2, 3 and 2, 1, right? But both these values when returned to their parent, this root will tell the parent that now I have 3 and 1. So now I have 4 leaf nodes which are at a distance of 3 from you, right? So this takes care of that, because again what I'll do for or the right map key value pairs, the same thing but with RMP in it, RMP of distance, right? So this is what the recursion tree we have done. Traversals is done. What is the question we ask in each node? Yeah, so again reiterating the third point, on each node what question do we ask? That is main. We ask to the subtree questions. We ask, give me a map of all distance comma frequencies of the leaf nodes you have. This is the question that we ask to each subtree. Now, mutually exclusive pairs, this thing I have already spoken about. So whenever we are considering a parent, right, 2, 4, 5 and 1, now whenever I have calculated for this much part, now for this much part only this much subtree has been calculated. So any leaf node which will be joining 1 in the pair, so 4 will be the left part only, and anything which is on the right part is supposed to be different always, in the sense it has never occurred in the solution set any time. Only 4, 5 might have occurred, but now whatever answers we are considering will be that we'll be considering one out of these, and then the other pair consideration will be towards from the left. So we'll be picking one value from right and one value from left. So this value will always be new, we have not calculated, and this value will always be already visited or calculated set. So we can say that any pair that we are adding to the answer, the step where we are doing over here answer plus equal to, any of the pairs will not be repeated over here. So we don't need to worry about repetitions. So answer plus equal to will have one value from here, one value from here, and then the frequency which we are multiplying it, right, it will do us all the frequency, like all the answer pluses 1 1 1 1 1 1 pairs, and give us the final combinations, unique combinations, if we consider one value from the right and one value from the left. So yeah, this was it. Coming to the code discussion. So as always, what I have done is I've considered a helper function first, right? Now that I have the helper function, we can just look what the helper function does. I've just initialized a map to be returned. This could have been an array also of sorts, but I have initialized a map to be returned. Now in this map, what is the base case? This defines my base case. Base case considers if the root itself is a null, then we can just return an empty map. Map does not have any feelings right now, we can just return the empty map. If now we know that that root itself is a leaf node, this is a leaf node case, then what I need to do is I need to tell that hey map, take in at a distance of 1, which is my d, and plus 1 value to it, whatever you had, which means it is equivalent to saying mp of 1 equal to 1, and these two are equivalent, and then we'll be returning that. So from any 2, 4, 5, what I mean to say is like 4 will also call left and right. Now the thing which will be returned is empty map. From here also it will be an empty map. So we don't have anything to calculate, so it will say that from here you will have 1, 1, which is the distance and the frequency. Then this was the base case. Then we do the post order. First we go to the left, then we go to the right, and then we calculate or process for the root. Now we are at the root. Now what we are doing is, for each of the pairs, in the sense, if I have suppose n values and m values in both the maps, left map and the right map, for each of those pairs in consideration, what I'll do is I'll check if the value, the distance value, this is my distance, this is my frequency. So now if the distance values sum is less than or equal to the distance, I know that I can take those pairs safely in my result set. So this is like giving the unique combinations as we had discussed earlier. Now the same thing here, we have calculated for the answer till here. Now we need to return also to my parent, right? Key, what is the increment in the number of leaf nodes and at what distance? So we have that. We have X number of leaf nodes right now, right? So for all the left side leaf nodes, what I am doing is I am checking if the distance is greater than +1, because if it is already like the distance is smaller, or even if it is equal to, then we know that anything from the left side will not get taken, because from the left side also we ideally need at least 1. Like if this value from the left side, distance is distance comma frequency map, if this has 3 already, then we know that if from here any positive distance comes, because distance can only be positive, any positive distance comes, so 3 plus x when 3 is positive and x is positive will always be greater than 3, so we don't need to consider that. So for that, the same logic over here, that we are adding the distance, because from here to here we know that the distance increases by 1. Again from here to here the distance increases by 1. So we are increasing the distance and we are adding how much frequency of those, like how many leaf nodes are there at that distance for the parent, and we'll be returning it to the parent. Similarly for all the left side, for all the right side map values, we'll be calculating it and then returning the map. Now I had taken a public variable. What other thing we can do is, here only I could have given the answer, and then I could have in star answer and then over here like this. So everywhere I have tried to keep ampersands wherever I can, so that whatever values that I'm accessing are accessed by reference and that do not take more memory. So yeah, that is the whole solution. Maybe someday when I revisit this lecture, I'll just short it down and then we can see where it takes us. Okay, that's done.